And okay, folks, can people hear me okay? Okay, great. Yeah, see some thumbs up. It's time, so I think I'm going to get going here. A couple housekeeping things. I sent out to 2 of the groups this morning a reminder that if you submitted them through Canvas, great, but I do need Word documents of your short lab report for the lab that you did during the 5th week, the 5th rotation. As soon as I get those, I will send out all 5 labs to the various groups. So, and hopefully today, if I remembered to bring them, I will scan and send back to you your, yep, and I have them here in my briefcase. I will send back to you my markups of your projects so that you have those to work on to get your project set to go. Next Monday, Kumar will be doing some lecturing. Week after that will be projects. And then the final day of class on the 3rd of May, we will be having you do your group lab report, basically synthesizing the 5 reports with different variables down. So that's sort of the lay of the land lab wise. As far as the lecture portion, I'll be with you today, obviously, and as well as Friday, and then the following week be with you. Basically, what I'm going to be covering in these 4 lectures is some, if I call it somewhat auxiliary types of items that we feel it's important for you to have some understanding of as you go out into your food careers. Today, I'll talk about fluid transport systems, basically stuff that gets real boring real quick to some people. We're going to talk about pipes and what do you make pipes out of? And trust me, most of you are going to sit there and be bored out of your skull. All I remember was when I took a class at Madison in auxiliary equipment, my first semester when I went back for my PhD, and I'm sitting there in class and I'm going, wow, and I'm writing down about 316 and 298 and all this stuff, white metals and stuff, and I could just see everybody else in the room going, huh, what's going on? Because it all made sense to me now because I was hired, and this is scary, and this is 70s, admittedly. I was hired because I had a master's degree in biology to be the quality assurance director in a dairy plant. I had never seen the inside of a dairy plant. Grew up on a dairy farm, so I knew the cow side, but I'd never seen, and I'm the one who's supposed to make milk safe for you guys and ice cream and cottage cheese. And so I was sort of learning as I went. One of the things keep in mind as you go forth in your careers, don't just hire people because you think. I was told, because I could get a master's, they figured they could train me to be the QC guy. And admittedly, you wouldn't do that today, but that was a different era. So enough background and so forth. So what I will be doing today is talking about elements in a fluid transport system in a plant, hopefully touching on some things that you can take away and just kind of file in the back of your heads mainly. And then if I have a little bit of time, I will start to move into refrigerator basics, which is the topic that is listed at the end of today, but specifically for me to cover on Friday. I always have trouble with this. Okay, now it's moving. I don't know why it is. I always have trouble getting the first slide to move. As I was mentioning to the one face-to-facer I have in class, I did this yesterday. I did 3 lectures, everything you wanted to know about food safety in 40 minutes. I did it 3 times for my daughter's a nursing instructor up at the College of St. Scholastica. And that's one of the elements in the nutrition class she's teaching. So what am I going to be talking about? We'll talk a little bit about piping and associated materials that go with that. Then I will move into talking about pumps and the different types of pumps that you're going to potentially be encountering within your careers in food plants. And then tanks. And most of you have been thinking about tanks because we're dealing with tanks to store your raw milk, to put your various products as you do your project. Okay, when we say piping and piping system, what do we have to think about here? Obviously, there are a lot of different types of pipes, and we'll get into more specifics about that in a moment. These pipes aren't always going to go straight, so we need elbows. The most common elbow is the 90-degree or the 180, where you take two 90s and hook them together. But if you're involved with designing or putting together a plant, you can off the shelf buy 30 and 60-degree elbows. But if you need others, you're going to have to make sure that you've got a good stainless steel fabricating company that is doing the work for you, so they can actually bend the pipes to meet the elbow requirements that you have coming. One of the things to remember with piping systems, that when you're putting piping systems into plants, especially into dairy plants, you just don't hook the pipes up and say, well, that's great. When you're initially designing that plant, you're probably going to have an inspector there who's going to be checking, especially if you use a welded system where you're welding pipes, elbows, and so forth together. They're literally going to be using what's called a borescope, or think of it as a fiber optic cable. And they're going to go in and they're going to look at that weld on the inside of the pipe, not just the outside. They're looking to make sure you don't have little burrs in there, little pits, so that things can get hung up. They want to make sure it's smooth so that you can properly clean it. And typically what happens, if they see a bad one, they'll take one look at you, and who's ever doing their work for you, they get out their torch and just cut that out of the line and start over again, welding things back together. So you have different elbows. Obviously valves, we've talked a little bit about valves, especially during first semester in the engineering class, but different types of valves to control flow. Allow fluid to go into a tank, allow fluid to leave the tank, and so forth. We use various restrictors, taking a 2.5-inch pipe down to a 2-inch pipe, or vice versa. Some of this is done simply because you want to build up more pressure. So you're pumping through a 2-inch pipe and you have the same flow through a 1-inch pipe, higher velocity, probably greater pressure. Obviously, flow meters. For those of you that did the pumping lab last semester, we had a flow meter on the system in order to tell us how many gallons per minute or liters per minute was going forward. And you could have all kinds of other things potentially put into your system. Now, when we start talking about the materials associated with pipes, the one that jumps to mind right away is stainless steel. Why stainless steel? Not because it's the cheapest, not because it's the easiest to work with, but because it is the best as far as cleanability. Not all stainless steel is created equal. You will hear people talk about 298 or 303 or 316 and other numbers associated with stainless steel. Basically, what most people use is a lot of 303. 303 has a low iron content. And one of the things, if you're wondering about stainless steel and you look at piping, we'll talk about white metal in a moment, they might look the same, but how do you tell the difference? What is one characteristic that stainless steel does not have? It is non-magnetic. You take a magnet, touch it to 303, 316, and the magnet falls off. It will not attach. There's not enough ferrous metal there to link up with it. 298 is used quite a bit, but kind of the norm a lot of people use, or at least historically have used, is 303. And then the 316 is the higher grade. It is a little more brittle, a little harder to work with. You don't gain a huge amount, but in some cases you may want to go that route. Besides the grade of stainless, you also have to deal with the type of finish, and the finishes are rated from 1 to 7. 7 being like almost a mirror. Why would you want to go higher in the scale? It gives you a much, much smoother surface, therefore easier cleanability in there, in your piping system. By and large, people would probably use 303 with a number 4 finish. You don't gain a huge amount with a 5 to a 7. Besides, after you clean it a few times and other things, you start to lose a little of that shine anyway. And so, while it might look prettier to begin with, probably not worth a lot as far as sticking all that extra money into it. Another type of piping material that you'll come across is something called white metal. White metal is, just as it would imply, it is whitish in color. It looks an awful lot like stainless steel. It is easier to machine. One of the problems with stainless steel, as I mentioned, is brittle. And therefore, trying to bend it, welding stainless steel is an art form. You don't just stick it together. I've soldered a little bit in my life, but I stay away from soldering at home because I don't want to cause a leak because I do a crappy solder job and my pipes start leaking in the basement. But stainless steel welding is a true art form. In order to get those nice smooth welds that I was mentioning that are going to be checked, you literally have to have a gas, an inner gas on the inside that in essence holds the weld from dropping. And so it's if you're a high-end, high-quality stainless steel welder, you can make lots of money. Not trying to tell you guys to, although staring there at a weld all day would drive me crazy, but there is big bucks to be made in stainless steel welding. But white metal is sort of that poor man's alternative. It contains a little bit more iron, so it would turn out to be magnetic and so forth. We do have a couple of valves in the pilot plant that are white metal. And one of the things you'll notice that they sort of take on more of a brass-like color over time, sort of some oxidation occurring in the metal. Basically, if you're dealing with dairy plants, everything needs to be stainless. And you may think, well, why do we have white metal in the pilot plant? As long as it was there when they stipulated that white metal was not to be allowed, you were grandfathered in, meaning you can leave it, but you can't replace it with more white metal. So it's something that is fairly cleanable and so forth, but it does nick a little bit easier, does have a little bit more bendability. Now you move into galvanized pipe. Galvanized pipe, when I worked in a soda plant, what we use galvanized for, that's where we pumped our sugar solutions. We'd unload it from the truck, pump it through the galvanized. Again, fairly inert. We didn't need to worry as much about potential contamination. And so galvanized worked well there. Black pipe. Black pipe, usually to me, I think black and I think sewers. So it's typically used for attachments as for waste streams and drainage and so forth. Copper piping, again, very typically used with water. One of the good things about copper, it is fairly flexible or bendable, but problem is you're all probably thinking copper is a pro-oxidant and you don't want too much copper in your plant because you don't want to be spreading all those copper ions around and oxidizing the crap out of your product. Glass piping, and there may be some of you already want glass. Why would we want glass? Because glass will break and glass can cause problems. And admittedly, not a lot of glass is used, but where is a good place to use glass? In your laboratories, for your drain pipes. Because if you're doing things like ether extractions, although you don't want to be pouring that down the sewer, that better be taken care of other ways. But if you're doing things that are involving acid extractions and so forth, even though you're probably disposing of it properly into a bucket, you're still rinsing out that Keldol flask or whatever with a little bit of acid in it. And with time, and this did occur to a company here in town called the Dairy Quality Control Institute. They did a lot of these types of extractions. And after a few years, they had to replace their pipes because the pipes had been corroded by the acid that went down the drain. So glass has its place, but admittedly, limited because of obviously the potential for breakage and thus contamination with glass in the plant. Plastic type pipes of various types. If you're in the pilot plant, you've seen all kinds of hoses. You've walked in there and seen them moving from point A to point B. Best way to think of plastic pipe, it's a great way to have flexibility in your plant, but you do not want to put plastic in place as your sole piping type of mechanism. It works great in a pilot plant simply because you're trying to hook day-to-day different configurations of equipment together. Whereas in a typical plant, you're not going to see too much plastic. Although on filling machines that go up and down, that you may be sucking off foam, a metal pipe obviously isn't going to work real well, so you need some flexibility there. The big danger with the plastic pipes is you have the plastic tube, usually a metal insert stuck in the end that is clamped very tightly. And the problem you have is you have that metal insert in there, and as tight as you can get it even, there's always a potential for product to get between the pipe or the plastic and the metal, and thus be a potential place for contamination for bacteria to grow and so forth. So you should, on a routine basis, disassemble that entire assembly, clean out the pipes. If you ever are in a QC situation, and I ran into this once in our dairy plant, it was on our defoamer on our filling machine when I worked in the dairy plant. Pulled off that pipe, you could just pull it out and you could smell that that's where the problem was. Again, all of these materials have their place. Stainless, again, wonderful for cleanability. White metal, very similar, and in a lot of food operations, it may be acceptable. Galvanized black copper have specific applications, and certainly glass in the laboratory and plastic materials. Again, just to touch on what are we trying to do in these pipes? We're either trying to induce turbulent flow or laminar flow. You're all aware of turbulent flow. When would you want turbulent flow? For cleaning, for heat exchange, where you need to move the product from the center of the pipe to the wall and back. Why would you want laminar flow? When you're in turbulent flow, not only is your liquid moving from wall to middle and so forth, molecules are banging together, especially if you have a complex system. Again, I always go back to my dairy roots. When you start banging fat globules together, what do you start creating? Whipped cream. And you don't want to do that. Or you have molecules scuffing off the membrane and oxidation can occur. And the same is true with other types of complex systems. You don't want things crashing into each other. So laminar flow, while you don't move as much volume, is more gentle. You're being kind to your product, and you want to be kind to your product so your consumer is kind to you and buys your stuff later down the road. You don't want to put crap in a bottle or crap in a bag. Okay, enough on piping. Now we'll talk for a chunk of time here on the different types of pipes. Or excuse me, not pipes, pumps that we're hooking the pipes to. One that is there are two very commonly used ones in the food industry, the positive displacement pump, and we'll talk later about the centrifugal pump. What is the benefit of the positive displacement pump? You can generate extremely high and consistent pressures. The pressure generated by, and we'll talk about the designs in a moment, but with a piston type positive pump, which is ones that are used to get really high pressures, you typically have a piston, it's either 3 pistons all of you have been around the homogenizer during the lab in the pilot plant for homogenization. And if you notice, one of those pistons, if you looked, was always pushed, was basically all the way in, one was all the way back, and another one was in the halfway position. So they're alternating. So what do I mean by a sine wave here? As that piston starts to move forward, to move liquid through the system, the pressure goes up, 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 reaches a max, and then it goes down, 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 down as the piston comes back. And so if you had a single piston pump, you'd go up and down, up and down. With three, think of it, it evens it out. One of them is all the way in, one is all the way back and getting loaded, and so they're evening things out. If you looked at that pressure gauge real close, you may see just a little bit of wiggle. But with three pistons and certainly with five, you're able to even out that flow. And if you're looking for 2,000 pounds per square inch of pressure, you can keep it probably within plus or minus 5, or maybe better, or maybe a little bit worse. So you need to get these high pressure. Important thing with a positive pump, the volume discharge, that is how much liquid is coming out, is independent of the pressure. I always say positive pumps have a one-track mind. You tell it to pump 400 gallons per minute or 30 gallons per minute or whatever you want it to be pumping per minute, and it goes, me pump 30 gallons a minute. I don't care what happens downstream. So what happens if you close the valve downstream? What's the pump going to do? Pump 30 gallons a minute, 30 gallons a minute, 30 gallons a minute. And you're thinking, what happens? Nothing good. The weakest link in the system will fail. You blow the face off the pump, you burn the pump up because there's no place for it to go. Seals fly, all bad things happen when you close the valve downstream. But the value is you get an even flow, which is great for metering, and especially if you're using long strokes, when you're trying to mix things from one tank to another, using a positive pump to meter that liquid in. If you're putting vitamins in somewhere, to meter those vitamins in. So the positive pump, that volume discharge independent of pressure, is something to keep in mind. Now, just to look a little bit at the hardware, this is a cutaway in some respects of a homogenizer. An homogenizer is basically the ones you used in the pilot plant is a 3-piston positive pump, which has a specific outlet, that being the homogenizing valve, where we're pushing that liquid through and taking that fat globule and reducing it in size to give us hopefully a stable emulsion. So basically what we have here, you've got a huge drive motor. Then you have a transmission of some sort. In this case, it's a V-belt. You've got a pressure indicator about what the pressure is in the system. Number 4 there is the crankcase, where one piston is pushed forward, one push is back, the other is in an intermediate position. Obviously the pistons have to have some type of carriage, some type of seal on them so that they can go through the stainless steel block that they're pushing through. Then at the very front, we have the little, what are called poppet valves in my terminology, where as the piston pushes forward, one valve is the one valve in front of it's pushing one down so nothing comes in. Another one pops up so it goes out through a discharge chamber. And then we have our homogenizing device and so forth. Again, another place that we used a pump exactly like this was in the membrane processing lab. To maintain those pressures, we had a small positive displacement pump, and many of you, or those of you that were there for lab, remember there was water on the floor. Well, one of the things you have to do, because you've got metal basically sliding through metal, is you need to maintain a cool environment or you just burn the pipes up. you'd freeze, the system would freeze, the metal would expand, and you'd have bad things happening. So that's what that water is on there as basically as heat removal. Another type of positive pump is the geared positive pump, and this one is probably more common than the piston because it's cheaper. Still, they're not real cheap, but they're cheaper. This was a type of pump that is part of the pasteurizer. When Lisa was going through talking about timing the pump and sealing the pump, what we have on the front of that timing pump in the pasteurizer is a lobed pump. And they come in either 3 lobes, you can have them in 2 lobes, 4 lobes, probably 3 lobes. So this is what they look like when they're kind of sitting there without a faceplate on. If you're looking at, we'll get to exactly how the flow goes through here in a moment. This would be the kind of the cutaway of the pump that we had in the pilot plant, as well as the other types of lobed positive pumps. You have a timing gear, if you notice on the top right of each of those 2 schematics. You've got a little nub that goes out. Well, basically what that is that's a shaft going to the motor that is turning it, where you're getting the energy put in, and it's sealing that motor that it can only run so fast that you're able to get the timing effect that we did on the pasteurizer. So basically you have a bearing system and so forth that allows transport of the transport of the energy to the lobes and moves the liquid forward. Now, if you're trying to envision how does the liquid flow through the pump, basically the 2-lobe pump here starting on the left-hand side, the liquid is flowing in. Notice that the lobes are touching one another, and that's the secret in here, whether it's 2 lobes or 4 lobes. These lobes have a very, very, very tight tolerance. They're machined very precisely. That's why these pumps can cost you some serious money, because as this liquid flows in, notice it's either transported up or down. Notice these 2 lobes are turning. As they move, they basically are creating, if you want to think it, pockets of liquid. And as that liquid fills the front cavity, it's moved to the second cavity and then pushed out. When you have a 3-lobe system, or excuse me, a 4-lobe system, you have more cavities. But the whole idea here is tight machining, tight tolerance in there. One little thing to file away in the back of your minds is that obviously with time, these will wear a little bit. And so you will get some slippage in liquid, kind of, if you want to think it, flow through the middle. And so if you set up a system to be timing at exactly the same time, and you take out your old lobes and put in new lobes, you will generate higher pressures. You will speed up the process. So for instance, in your dairy plant, if you change out the old lobes for new lobes, you probably are going to be the liquid will be flowing faster than 15 seconds. So if you make those kinds of changes, make sure you check if it's a regulatory issue with your regulatory people to make sure the timing is correct. But if you're using it for metering, you need to make sure that you're metering at the proper amount. Otherwise, you're going to have some kind of funky product that's going out the back door, so to speak. I put this in just to give you a little bit of an idea of what is happening inside of each of these piston strokes when the piston comes forward. If you notice, what you have is you have this sapphire ball bearing in this picture I could find. Probably don't want to use sapphire ball bearings. Typically, these would be stainless steel valves of some sort, stainless steel machine material. But basically what happens is that as the piston goes in, the top arrow, it applies pressure to the liquid that has filled the cavity, that blue liquid. As the pressure builds up, what happens? The liquid pushes down on the bottom bearing and stops liquid from flowing in while it pops the other one up and pushes the liquid out. When the piston has reached full extension and it starts to move back, what happens? Oh, you have a spring load on the top ball bearing and it pops it down because you now are kind of creating a vacuum in there, in that chamber. And what happens? The liquid flows from the bottom, whether you're using a big tank where there's a pressure from the tank or a booster pump to get it there, it pops that little bottom ball bearing up and liquid flows in. Piston gets all the way back and it all starts over. And you could see we're putting these in series, 3 or 5 pistons, where you get that evening out, that sine wave effect occurring. This is just a picture I found that kind of ties together all kinds of different pumps that you might come across. The first up there being a depiction of a piston pump. Second one as well, a gear pump. So basically variations on a positive pump. Over on the top right-hand side is a rotary pump, which is kind of, again, a variation on a centrifugal, which we'll talk more about in a moment. The rotary in this case has blades that tend to be able to generate higher pressures because they seal the cavity off. If you notice, it's touching on one side, open on the other, so the liquid is able to flow in. We have what's called a jet pump, which is really using a pump to add extra velocity and flow through the system. Airlift pumps, where literally you pump air in to cause liquid to flow. Probably not something you're going to want to use too much of. I've never seen one in a food plant. I assume they're there. Why don't you want them in a food plant? We don't want all that air in there, unless we want to sell more air, to be facetious about what we want to sell to the public. But we need to keep the air out again, minimizing lipid oxidation and so forth. The bottom left, a propeller pump, which just as the name implies, kind of like a motorboat, pushing the liquid out. And then the centrifugal. I always look at the centrifugal and depict it as the workhorse of the pumps in the food plants. And what does the centrifugal look like? The suction eye, what's there, that is where the center of the pump is. That's where the pipe would come in, where the liquid is going to flow into the pump. Then we have a series of impellers or propellers, or whatever term you want to use. This is sitting inside of a casing. And off of these propellers, we have vanes. And this propeller is spinning at high speed. So the liquid is being sucked in. Literally, this is called the suction side of the pump. It creates a vacuum. It will pull the liquid in. As it's pulled in and it's spinning around, it's imparting energy and pushing the liquid out and discharging it. If you go to buy these pumps, you can get variable speed centrifugal pumps, but by and large, what you're probably going to see is 1,600 or 3,200 revolutions per minute for speeds, to sort of speak, if you want to say, buying it off the shelf. When would you use one versus the other? They both can move a lot of volume. The reason you would consider a centrifugal over a positive, if you don't need to worry about constant pressures and so forth, you can move a lot of volume a lot cheaper with a centrifugal. Centrifugals aren't cheap, but they're certainly cheaper than getting, you think about the makeup of this pump, which you've got some motor back there, which think of the mechanical design of a positive pump, all the things you have to consider there. So 1600 would be probably something you would use when you want to move product. Because again, you don't want too much turbulence, but again, we got to move it so we can sell it. So you want to use a little gentler approach. 3200s, very often people will swap one pump out for another pump in cleaning systems because you want to get high speed, high turbulence for that scrubbing action that you're going to get when you run your product through the pipelines. So that chlorinated alkaline cleaner that you're using is doing the job that you want it to do. One of the things though about a centrifugal pump is if you look here on this graph, head pressure, basically how much pressure is that liquid encountering versus the volume that is flowing. And what will happen is as you're pushing the liquid further and further down longer piece of pipe or up higher and higher, the back pressure of the liquid will slow down the amount of liquid that is being pumped out. You literally could take a centrifugal pump, put a standpipe on it, and start pumping, well, let's just say water into it. As you pump water into it, sure it moves, but if you kept adding more and more and more pipe, you eventually would reach a point where the column of water would be pushing down with sufficient pressure that nothing would flow. It'd just come to a standstill. So you're going to get, that's the thing you get here with the centrifugal. You have this variable amount of liquid that can be moved depending on how far you're pumping it, how high you're pumping it, and so forth. But in most cases, in most plants where you can live with some variability, you aren't worried about all this timing thing to the last millimeter, so to speak, or milliliter of liquid coming out, you should be fine with centrifugals. And again, a lot cheaper to buy. Okay, enough on pumps. What we'll spend the rest of the time today is talk a little bit about tanks and various types of containment vessels for our liquid. This is just a side cutaway of a tank. A lot of our tanks in plants, anywhere from small ones, those guys, the people that are doing ice cream mix making have got, I think they're using 100 gallons, but you could be using small 50-gallon tanks to add their flavorings. Those of you that are adding other ingredients, using other tanks for mixing. Basically, this tank, fairly simple design, stainless steel shell with a propeller, motor up on the top to generate the flow. You've got a exit or at the bottom on the right-hand side, excuse me. And you have an access port up on the top so that you can get into it if you need to get into it. The design of the propellers in there can be all over the place. This I put in because it's a very complex propeller system. Why would you want to put all of that stainless steel in there? Somebody might be thinking, how the heck am I going to clean it? And that is an issue. How are you going to clean it? But this would be a great type of tank if you need to get and mix a lot of ingredients together to make sure you've got good distribution. For instance, a group that's doing chocolate milk, probably not this complex, but you need to put in milk, you need to put in chocolate, you're putting in stabilizers. Probably don't need, as I said, this many agitators, but you need something to get good flow to make sure that things are properly mixed. So this would be more of the vertical vat mixing type tank. Typically in plants, probably once you get up to 1,000 gallons, maybe 2,000 gallons, you're kind of maxing out. You don't, the batch size, once you get around 1,000 gallons is getting to be pretty good size. But again, depends on what you're mixing and all those types of things. Now we'll move more to what I would consider the family of storage tanks, places we can put liquids to let them sit as we move through the process of making various products. This is the stainless steel vertical tank, very common. On the small side, typically you get up to about 20,000 gallons, and that's about as big as you want to go with a vertical tank. We're going to want to get into the horizontals as we move forward into greater and greater volumes. This is a schematic of different types of elements that you might see in a vertical tank. The main things to note, number 13 there is some type of access port so that you can get into and out of the tank if you need to. I mind you that once you open that and you go to get in it, you need to be thinking about your safety. Because what is the environment like inside? What gases might be present and so forth? In the state of Minnesota, by law, the Minnesota Confined Space Act, you're not supposed to even stick your head in there without a breathing apparatus available. Because, and you're thinking, well, it's a milk tank in our pilot plant, no big deal. But do you know what's in it? What happened if there were somehow extra chlorine sanitizer got in there and you stick your head in and take a good whiff of chlorine gas? Not going to be too good for you, but you have the access. Up near the top up there in that area of 8, 11, 16, you have a viewing port so you can see what's going on. 16 up there is something very important, not only in vertical tanks, but in horizontals. And that is some type of way of venting, of having air equilibration. And why is that important? Think of this as a sealed vessel. No way to get anything in. And I start pumping out down on the bottom on number 8. And I'm sucking it out of there. What's going to happen inside that tank? I'm going to be removing the liquid. I'm creating a vacuum in there. And you need, if no air comes in to balance it out, what happens to your tank? I watched a guy suck a bulk truck in one time. He didn't put a vent on the top. He got talking to somebody and forgot to put the vent on and started pumping off and literally sucked the walls in. And that's what will happen if you don't have proper venting. You may be thinking, venting, that's not so good because we're sucking air in. You need to make sure that it is sanitary. But that's something that's very critical to think about. If you ever suck, if you're working, you suck one in, you might as well just go to your boss and say, I'll check out, send me my paycheck. I know I'm going to get fired because I broke the tank. But then again, a lot of other pieces of things here. But again, you have that venting and visual on top. Number 8, it could be your fill ports. You could fill through the bottom, but a lot of tanks, you may put liquid in through the top. But the thing to keep in mind is if you're pumping through the top, you don't want things just splashing in there. Usually they use what's called a gooseneck, which is sort of a curved piece of metal. The liquid goes in, curves over, hits the wall of the tank and flows down. So you're trying to avoid air incorporation into your product, a more gentle way of putting it in. You could fill through the bottom as well. Now, once we get beyond maybe 20,000 gallons and you need to store a lot of product, many of you with your project, you're in the realm of 50, 60,000 gallon tanks, you're going to be using silo tanks. Why a silo tank? Well, first of all, you can put a lot of liquid in it. And you can think, well, I could have a big horizontal tank too, but think of how much floor space that big horizontal's taken up. Even if you stick it out the back of your tank, out the wall of the plant, and have all the access and everything on the inside, you still need a lot of footprint for it to sit on. The value of the silo tank is you do your storage vertically. You're putting it up in the air. How big can these tanks be? 50, 60. I saw one when I was in Morocco in the 1980s. It was, I think they said there were 5 million gallons of orange juice concentrate in it. It was a massive, massive tank. I still don't know how that tank stayed together, but back to here. Silo tanks, very common from that perspective, that you're able to put a lot of liquid in a vertical space so that it makes it easier for storage. Also, these can be sitting outside your plant. In other words, as long as you've got it sealed properly on the outside, you don't have to worry about necessarily super cleanliness. If it's inside, again, there's big vertical tanks in the plant, you got to keep them clean. The inspector sees dust on them and you're going to catch hell from the inspector. The expectation is you don't have dirt buildup. Here, if it's dirt on the outside, as long as you aren't getting it in the product, you should be good to go. This is just to give you an idea of what it's going to look like on the inside. Over on the right-hand side is basically your access area. So you would have an access door. You would be able to fill into the tank at this point. Probably want to bottom fill silo tanks. It's a long splash down from up on top. But if you notice that number 14 there, that's your air equilibration. As you suck out, you need to bring air in to replace that volume inside. You don't, bad enough to suck in a bulk truck. Imagine sucking in a 100,000 gallon silo tank, crunching it up. Just think of taking an empty soda can and squeezing it. Crinkles real quick, and that's what can be happening in here. One thing I forgot to mention with respect to the vertical tank, as well as it's true of the horizontal tanks, basically, these kind of come in two ways. Most of the time, they are a vessel that will maintain temperature. They're not designed to cool. If you're going to want to use, if you need to cool something to put in these, you need to use some type of plate heat exchanger, tubular heat exchanger to cool that liquid down. What these will do is typically have what's called a cold wall. So maybe 5 feet, 10 feet up, you'll actually have refrigerant so that as the liquid is mixed in the tank, slowly mixing it with an agitator, you can maintain temperature. If you go in our pilot plant, the milk tank that is used that feeds the pasteurizer, it has what I call a cradle. So a little on the bottom of it, there is a refrigeration contact surface to maintain temperature. Could you pull temperature down? Yes. Would it take a long, long time? Yes. So something to think about there. Just a picture of silo tanks at a plant. If you notice down on the left, on the right-hand side, that little white square, that is what's sticking into the plant. That is where you're able to access it, put product in, take product out, and so forth. On the top up here, you've got different types of an access port if you really, really needed to get in from the top to do something, as well as other mechanical materials hooked up. Could be that you're running your refrigeration from the outside as well. Another truck that you're going to see a lot of, regardless of whether you're dairy or whatever, buying sugars, is the over-the-road tank truck. Most of these over-the-road trucks are simply rolling thermos bottles or rolling vertical tanks. You have access at the top. At the back over here, you've got a panel that'll open, which will allow you to hook up a pipe that'll allow you to have liquid flow out and so forth. The bulk of these, typically it's a stainless steel inner shell, anywhere from 5 to 10 inches of foam insulation with a stainless steel outer shell. What is it? It's a big rolling thermos bottle. 5,000, 10,000 gallons of rolling thermos bottle. Some are refrigerated. How do you know if it's refrigerated or not? Look at the truck end where it's hooked up to the truck. And if it's refrigerated, you'll see some type of what'll look like an air conditioner there. And that is what is taking the heat out of the liquid that is in the cradle that would be in there cooling it, replacing it with colder material, which is actually a good segue for us, what I'll be talking about next time, which is refrigeration. But again, think of these as nothing but 5,000 gallon, typically rolling thermos bottles going down the highway. And with that, I'm out of time. Sorry, I'm a minute over or two. Hopefully this gives you kind of it's a whirlwind tour of the wonderful world of tanks, pumps, and all kinds of piping junk that's hooked up with them. So with that, I'll be here if people have questions. Otherwise, do look for your, I'll go up and scan and send out today the drafts of things. And again, the two groups, please get those reports to me so I can get everything out. So with that, I will sign off or sit here, and when I don't see anyone, so be it. You want yours?